In the last video, we looked at division of integers from a divisibility perspective. Now we're going to look at division of numbers when the result doesn't happen to be an integer. So we're going to think about quotients and remainders. We're going to reflect on patterns of quotient and remainders from our arithmetic experience, how we find them, and what kind of equations they give us. We're going to summarize our observations in a theorem, and then we're going to start thinking about the first steps in proving the theorem by discussing the well-ordering principle. So we know how to handle a problem like 21 divided by 7. We know 7 times 3 is equal to 21, so 21 divided by 7 is equal to 3. This is exactly what we were doing when we were talking about divisibility of integers. So the question is, how do we handle a problem like 14 divided by 3? And there are two reasonable answers to this question, or at least two, I should say. So we can handle it like a rational numbers problem. We can extend the integers to rational numbers. We get 14 thirds, perfectly good rational numbers. That's not what we're going to do because we're kind of sticking with an integer-based approach. So we're going to set some rules for finding quotients and remainders, which are all based upon integers. So when we do 14 divided by 3, we're going to first find the biggest integer q that we can, such that 3 times q is less than or equal to 14. So it's less than or equal to 14, but the biggest quotient that we possibly can. So in this case, it's q equals 4, because 4 times 3 is 12. If we do 5, that's going to give us 15, which is bigger than 14. That's going to be what we call the quotient. Now, if we want to get the remainder, what we do is we take our quotient times 3, that's 3q, subtract that from 14, that gives us the remainder, so we get 14 minus 3 times 4. 14 minus 12 gives us 2. So when we do this division problem from an integer perspective, we get a quotient of 4 and a remainder of 2. So we can, of course, generalize this to any division of any two integers, right? As long as we're dividing by a number that is bigger than 0. So first we find the biggest integer possible, q, such that aq is less than or equal to b. We're dividing by a, so we're looking at multiples of a that give us less than or equal to b, but we can't get any bigger. The q is going to be what we call the quotient. And then we're going to subtract that aq from b to get the remainder. So we get the remainder r is equal to b minus aq. And if we wanted to, I mean, there's no reason that we have to, but this is how it's going to be stated in the theorem. That equation, r equals b minus aq, is completely equivalent to the equation b equals aq plus r. Those are the same equation, just written in a different form. So our summary is that when we do division of integers b divided by a, we want to find a quotient, q, and a remainder, r, such that b equals aq plus r. We want to make q as big as possible, such that aq is less than or equal to b. And once we know q, we can immediately get our remainder, which is b minus aq. So I want to talk a little bit about our rules for finding quotients and remainder. So first of all, the equation b equals aq plus r is the fundamental thing that expresses the relationship between what a quotient is and what a remainder is. The second thing is that whole deal with making aq less than or equal to b and making q as large as possible, those seem like reasonable things to do, but in a global sense, they're completely arbitrary. They're rules we just made up, right? If I was in a different universe, I might make up different rules about which quotient, which remainder that I might have. And as long as I had b equals aq plus r, those would still be reasonable rules. But these are the rules that we think are the most reasonable. And the third thing is that when I say make aq less than or equal to b, that makes our remainder, b minus aq, a non-negative number. Right? If you're subtracting b, a bigger number, minus aq, a smaller number, that's going to give you a non-negative number. And since q is as large as possible, that makes that aq as large as possible, right? That means when we're subtracting b minus aq, we're making that, the remainder, as small as possible, right? When we subtract the largest number possible, we're making the number itself as small as possible. So then the question is, what are the possible values of r, the remainder, under our rules? Well, I'm going to sort of lean on your experience in doing these problems back in your elementary days about what kind of remainders you get. So for instance, if you were to divide by 3, you would expect to get pretty small remainders. Remember, you're finding your remainders as small as possible. They got to be non-negative, so at least 0, but as small as possible. And you probably remember your experiences being you got remainders like 0, 1, and 2. If you were to get a remainder that was 3 or bigger, that probably meant that your quotient wasn't big enough. So if you made your quotient bigger, that would make your remainder smaller. And if you kept doing that, you'd get a number that was 0, 1, or 2. And similarly, if you divide by 4, you'd expect your remainders to be 0, 1, 2, or 3. Again, if you got a remainder that was 4 or bigger, that probably meant that your quotient was too small. So in general, if you divide by a positive number a, your remainder is going to be, well, 0, 1, 2, some number between 0 and a minus 1. So your remainders can't be as big as the thing that you're dividing by. So here's our theorem. We haven't proved it yet, but let's write it as a theorem anyway so we know what we're aiming for. So let a and b be integers such that a is a positive integer. And so we're dividing b by a, remember here. Then there exists q and r in the integers. And again, we're thinking of q as the quotient, r as the remainder, such that b equals aq plus r, and r is between 0 and a minus 1. So I want to make one last remark about remainders. If we ignore our arbitrary rules about remainders, about aq being less than or equal to b and q being big as possible, then the remainders are integers of the form r equals b minus aq. So if we're looking at remainders without our other rules, that's exactly what a remainder is. And you can see there's a ton of remainders. There's a different remainder for each value of q, right? Where q is an integer. So if we want to collect the set of all possible remainders, we get the set of all x in the integers such that x is equal to b minus aq, and q is an integer, right? So that's the set of all possible remainders. Now we're going to be interested in our division algorithm for non-negative remainders, and even then, even if we just set the rule of we want the remainders to be non-negative, that still doesn't narrow down the remainders very much. There's still going to be a ton of remainders possible. Then we can express that set, and when I say non-negative integers, that's the same as saying whole numbers, right? So we're looking at x in the set of whole numbers such that x is equal to b minus aq, where q is an integer. Again, q doesn't have to be a whole number, but when I plug in q into b minus aq, that should give me a whole number. So that set is going to give us all the possible remainders that are non-negative. All right, so now I want to take a little shift into something that is going to do a couple things for us. It's going to complete our integer axioms, and also it's going to be a really useful tool in proving the division algorithm. So remember our integer axioms. There was a bunch of them, so I'll review. So for arithmetic, addition, our integers are closed under addition and multiplication. Addition and multiplication are both commutative and associative. We have the distributive property. We have an additive identity and a multiplicative identity, 0 and 1. Every integer has an additive inverse. And for our order properties, we have trichotomy. Every pair of numbers can be compared. We know which one of them goes before the other. We have transitivity, the transitive property. And we have translation invariance. In other words, if you take an inequality and add the same thing to both sides, the inequality stays in the same direction. And finally, we have scaling, which means if we multiply both sides of an inequality by a positive number, then the inequality stays in the same direction. And remember, our issue with these axioms, or at least our issue with just these axioms, are that they don't distinguish the integers from other number systems like the rational numbers and real numbers. The rational numbers and real numbers satisfy all those axioms as well. So if I say I'm thinking of a number system that has all these axioms, I haven't narrowed it down. You can guess more than one and be correct. So what I want to do is add another axiom that will distinguish the integers from the rational numbers and real numbers, and in fact basically from all other number systems. Well, let's see. So we got to ask ourselves, well, what else is there that where z is, the integers are different from the rational numbers and the real numbers? Well, the big most important thing that we're going to be looking at is there's lots of space between integers. And what do I mean by that? Well, if I take consecutive integers like 1 and 2, there's a big space between 1 and 2 where there are no integers, right? So if I take those two consecutive integers, there's lots of space in between there. Whereas if I take two rational numbers like 1/4 and 3/4, there are going to be infinitely number of rational numbers in between there. And even if I make the rational numbers super close together as I can possibly imagine, there are as long as they're different, there are still going to be infinitely many rational numbers between there. The same story goes for the real numbers. So in the integers, you have this notion of consecutive integers, one that comes right after the other and nothing in between, but you don't have that in Q and R. So our new axiom is going to sort of pick up that idea of having space between consecutive numbers. So here's another way of seeing kind of the same thing. If I look at the real numbers, and if I let S be the set of all just positive real numbers, real numbers that are greater than 0, there is no smallest element, right? Basically what I'm saying is look at all the real numbers that are to the right of 0 on the number line, and there's no number that's right next to 0 that's positive. Any positive number, there's going to be a ton of real numbers between 0 and that number, so we could pick a smaller one that's also bigger than 0. And we can do this no matter how teeny tiny that positive real number is. However, this sort of thing does not happen with integers. So here is an additional axiom for integers. This is the one that distinguishes integers from all other number systems. It is called the well-ordering principle. Right? So it's an axiom. It means we're assuming it. So here we go. So let S be any non-empty set that does not contain any negative numbers. In other words, it may contain 0. It may contain positive numbers. It doesn't have to contain all the positive numbers. It doesn't have to contain 0, but it only can contain positive numbers or 0. Then S has a smallest element. So, for instance, here's a set that is not relevant to the well-ordering principle. If I look at all the integers that are less than 4, that does not have a smallest element, right? There's a ton of negative numbers, but there's no smallest negative number. There's no negative number in saying, okay, -1,000,000, that's the smallest one. No, it includes all the ones to the left of -1,000,000 as well. So, but that's not relevant, right? I mean, it has lots of negative numbers. The well-ordering principle only applies when you have non-negative numbers. All right, so that was kind of weird. All right, well, if you look at this set, the set of all integers that are greater than 4, that one does satisfy the requirements of the well-ordering principle. It only contains it doesn't contain any negative numbers. That one does have a smallest element, and the element is 5. So even though the definition of my set is x greater than 4, right, I can still find a smallest element of 5 because there are no elements between other integers between 4 and 5. And the set itself does not contain 4. However, if we take that set x greater than 4 and say, well, x doesn't have to be an integer, it could be any real number or any rational number, then there is no smallest element. If we look at all the rational numbers that are greater than 4, there's no smallest one that we can have, and same with real numbers. So what we're going to do with this well-ordering principle is we're going to apply it to non-negative remainders in the division algorithm, and it's actually going to help us a great deal improving that theorem. All right, so now I think you're ready to start working on the activities for the division algorithm on the PDF file included with this video. There's 2 more videos related to the division algorithm, but right now you're in a good position where you can start.